So now let's look at E1 eliminations. And one of my favorite sayings in terms of organic chemistry is to find similarities and differences. E1 eliminations are still eliminations. So we're going to find that we're still forming double bonds. It's just the mechanism is going to be a little bit different. Also, the relationship between E2 and E1 is almost the same as SN2 and S1. So E1 eliminations means that we are going to do unimolecular, it's unimolecular reaction. And so I expect to form a carbocation here. So we're gonna see this in just a second. But overall, the elimination is the same. So when I look at an E1 reaction, I kick off the leaving group, I kick off an adjacent hydrogen. So say in this case, I'm going from a CH3 to a CH2, and I draw a double bond across there. So I end up forming a double bond. That's true. When I do an elimination, leaving group, adjacent hydrogen, draw a double bond across there. The difference is going to be in the mechanism. So here, just like an SN1 reaction, when I look at the rate law expression, the only group that is inside of there is my electrophile, my group with a leaving group. So this, when I say T, BU, BR, I am talking about this species. So there's the only species that's involved in my rate law expression is the one that has the halogen. So there is only one molecule involved in my rate determining step. It's going to be unimolecular. This is why it's called E1. And so the steps are going to look very similar. So, and then we can also tell this by looking at the rate law expression. There's only one species. It's implied first power. That's what we mean by unimolecular. The overall order of this reaction is first order. That's what makes it a unimolecular elimination. So what happens is this molecule spontaneously forms an alkene. And this can happen in reactions. And this is one of the things you should remember if you go on to become a scientist. You don't want to leave molecules dissolved in solvents for very long because they can spontaneously undergo a reaction, and this is one of them. Literally, the molecule just falls apart and forms a double bond. So remember, during an elimination reaction, there's two main steps: kicking off the leaving group and kicking off the adjacent hydrogen, and in doing so, forming a double bond. So in an E1 mechanism, these are broken into two steps. So remember, in the SN1 mechanism, the overall substitution was broken into two steps, and an E1 mechanism, the formation of the double bond, is formed in two steps. So just like the SN1 reaction, the first step involves leaving group removal. So what happens is the electrons from this CBr bond attack the bromine, and the bromine is kicked off. So with this, sometimes people will put a Br minus over here as part of a product, but mainly the electrons are leaving this carbon and we form a carbocation product. So notice that we make the same reactive intermediate in E1 as we did in SN1, and so that's going to be important. We'll talk about that more in just a minute. So during the first step of the E1 mechanism, we form a carbocation. In the second step, we now kick off the adjacent hydrogen. These electrons from the CH bond snap down, and we end up forming a double bond between the two carbons. So we form our alkene. In doing this, we also kick off a hydrogen in H+. So this is the idea of doing an E1 reaction. We still undergo the same basic steps, kicking off an adjacent hydrogen, kicking off the leaving group, forming a double bond, but in this case, it's broken into two steps. And so that's going to change things a little tiny bit. But notice, it doesn't matter if it's E2 or E1, we still have to have an adjacent hydrogen for this reaction to occur. Just like E2 reactions, Zaitchev's rule is in effect. So it doesn't matter if it's E2 or E1, the predominant product is going to be the one that is the most stable. So remember, you look at conjugation, number of alkyl groups, cis and trans, and it'll still form, the predominant product is going to be the most stable one. So here I give you a molecule, I say this reaction, I'm telling you that it's E1. The steps that you undergo to go from reactant to product are exactly the same. I find my electrophilic carbon, the carbon that's attached to my halogen. I then find adjacent carbons, so there's actually three. 1, 2, 3. And then I look for hydrogens on them. So yes, this carbon has got 3 hydrogens, this adjacent carbon has 3, this adjacent carbon has 3, this adjacent carbon has 1. So I kind of expect to form 3 products. In this case, I'm telling you that these two CH3 groups are equivalent, so they're exactly the same. If you get nervous and you draw one more product where the double bond's going up here, that's fine. It's a little tricky to see that these two CH3 groups are the same. By that I mean it doesn't matter if I put the double bond down here or the double bond up here. They're actually the same molecule. That's what I'm trying to say with equivalent. But so if you go ahead and draw out a third product, that's no problem. So how do I go from reactants to products? Okay, so I find my electrophilic carbon. I find my carbon with adjacent hydrogens. I remove the leaving group, and I remove an adjacent hydrogen, so we go from CH3 to CH2, and then I draw a double bond across here. So what's left over? So this carbon is this carbon. I go from CH3 to CH2. I removed an adjacent carbon. What's going to be coming off my original electrophilic carbon? So this carbon here is that one there. What's going to be coming off the double bond is a CH3 and then this CH2 methyl groups. So here, this carbon, remember this electrophilic carbon is this carbon. What's coming off of there is the CH3 and the CH2 methyl groups. The other adjacent carbon, so this is my other adjacent carbon. I only have one hydrogen on there. I remove the leaving group, I remove the adjacent hydrogen, and then I draw a double bond across here. What's going to be coming off my original electrophilic carbon is two CH3 groups. So I kick off the leaving group. I have two CH3 groups here. That's going to be coming off my double bond, two CH3 groups. Here I remove this hydrogen, forming a double bond across here. What's going to be coming off of this carbon is two CH3 groups. So this carbon is this carbon, two CH3 groups, two CH3 groups. Then the same thing, I say which one is going to be the preferred product. I say, is there conjugation? No, I need two double bonds to do that. Then I count alkyl groups. So this molecule has two alkyl groups coming off of it. This one has 1, 2, 3, 4 alkyl groups. 4 alkyl groups is more than 2. So this is going to be my predominant product. So when we look at this, one of the things I want to remind you guys, and what we're leading into, is combining these all together. So we're going to find out elimination and substitution reactions are linked by the fact that they all use halogens. And so we need to come through and say what reaction's happening. One thing I can say is that E1 and SN1 reactions are actually linked together. So the idea is, for right now, I can't have one without the other one. The reason why is they both have the same carbocation intermediate. So when I look at this in the SN1 and E1 reactions, the first step was the same. The halogen pops off and we form a carbocation. And then now it depends, once we form the carbocation, it can either gain a nucleophile and do an SN1 reaction, or I can kick off a hydrogen and do an E1 reaction and form an alkene. So the idea is, because both of these reactions have the same reactive intermediate, they're linked together. So I cannot have one without the other one. So I cannot have an E1 reaction without an SN1 reaction. And we'll take a look at what that looks like here in just a second.